Hello and welcome to Tiny Code Christmas Day 9. Today we're going to be looking at the classic demo scene effect, the Shade Bob. Oh, wrong Bob. The Shade Bob. And in addition to taking a look at this in TIC-80 and Poke, in TIC-80 we're also going to take a look at the peek and poke memory functions as well. So we're going to start with TIC-80 and you can skip ahead for Poke. So the first thing that we're going to do is take a look at some organic movement for our X and Y coordinates here. So I'm going to use the technique that we introduced yesterday, Lissajous curves, where we essentially get the sine and cosine of different angles and plot them as if they were a circle, and it ends up going all sorts of different ways. So instead of using sine and cosine, since we're getting the sine of different angles, it's not going to make too much of a difference, so it will actually save us some bytes when we go to make this smaller if we don't use cosine. So we want to take a look at these values in action, and I'm going to use circle XY, I'm going to give it a radius of 5 and color 2, and we'll just take a look at these values that I put in here, and obviously they're modified by the time so that we get a different angle every frame. So that looks nice and organic, and again you can see from the differences here, if I just maybe make that 2 and 3, or 1 and 7, that you can get all sorts of different types of motion. And to make the path a little clearer, what I'm going to do is remove the CLS, and you'll have to do this as part of the effect anyway. I'm going to clear the screen once outside of the function, outside of the TIC function, and then inside the TIC function I'm just going to draw circ. So you can see here that it doesn't clear the screen and it continues to draw the circles. So that is one potential movement pattern that you can get, and I'll change this to maybe 5 and 8, and you see you get something like that. So they're good to mess around with and to pick out something that's particularly nice. I'm going to stick with these values. They're multiplied by 110 and they're multiplied by 60, so that sine value is going to give me a value between obviously -1 and +1, and when I multiply that by 110, that will either add or subtract a maximum of 110 from 120, and 60 is the same, that'll be plus or minus 60, and 68. So that is our pattern that we're going to go with here, and it's nice, it covers pretty much a good coverage on the screen, and it's not a pattern that's going to repeat itself until it has done most of the screen as well, which is a good one. So it's actually going to give us good mileage in our effect rather than just piling back up on top of itself. Now, one thing that we have to do is we have to actually read every pixel, and then we have to get that color, we have to add 1 to the color, and we have to write it back to the screen. So we're not going to be using circ or rect or any of the built-in functions to do that, because they don't have the support for it. And instead, what we're going to do is we're going to write our own code to draw a rectangle. Well, we're going to draw a square technically, but this should be no problem to you, since we wrote our CLS clone in the early days of TCC. Instead of doing it for each pixel on the screen, we're just going to do it for a -4 to 4, -4 to 4, and I'm going to plot these pixels. So that'll be X plus I, Y plus J, and I'll just give it the color 2, and now we can see that we actually have a square moving around the screen, and that is a bit easier to see if I clear the screen. So your challenge is to modify this code here so that it reads the color, and you can use the pix function to read the color as well, check the documentation, add 1 to it, and use the pix function to put that new color back on the screen. And then you have some choices as to whether you want it to wrap around, so it goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and goes back to 0, or whether it stops at 15 as it did in our example. So the second challenge is to keep it to a maximum of 256 characters, and we're going to make an assumption there that you might want to play around with adding a palette. and we're going to talk about that as part of the section on the poke function shortly. There are some expert challenges up on the website that you can tackle as well. The character limit for that is 128, and there is some extra criteria there as well, so make sure that you check it out. And we are going to take a look at the peek and poke functions, and we're going to take a look at how they work. So first thing that we're going to do is we are going to poke the video RAM in TIC-80. So starting at memory location 0, the VRAM for the TIC-80 is laid out, and we can access the screen memory while using the poke function. So instead of using the pix function to set a pixel, I can poke memory location 0 with 2, and if I run it, you'll see that I have set the 0 memory location, which is x0, y0, to that color 2. Now, I've also set the next pixel to black, and that happens because when we're using the poke function, it will write 8 bits. The colors in TIC-80 are only 4 bits, 0 to 15. You only need 4 bits to represent the colors, the color index in TIC-80. So when we poke, we're poking 8 full bits. Now I can specify 4 in the poke function like this, and now I can, let's say, move to pixel number 1, number 2, etc., and we'll see that it will only write 4. We can of course use the poke 4 function instead, and that will save us 1 character when we want to work with the screen memory. You can of course use shift operators and OR things together to write the full 8 bits of color, but it's easier to just use the poke 4 function specifically so that you're poking in 4 bits of memory. The memory addresses that we would have to access if we're using poke 4 are then essentially halved, because instead of accessing memory location 1, which is 8 bits, memory location 2, which is 8 bits further on from that, memory location 3, which is 8 bits further on from that again, we're going up in 4. So memory location 1 will be 4 bits from 0, 2 will be 4 bits from 1. So in order to access a specific memory location, if you need to with poke 4, you essentially have to double it because you're counting in 4s instead of 8s. So let's revisit our clear the screen function that we wrote back on day 3. We used the pix function to clear the screen, and now we're going to do the same, but we're going to use a for loop. We're going to use I equal to 0, 3, 2, 6, 3, 9, do. I'll add my end, and I'm going to poke into memory address I the color 2. So now we've written some clear screen code that uses the poke function to set the pixel color of the screen instead of the pix function, or instead of using the clear screen function. Now that's easy when the memory is laid out in a linear fashion, but what do we want to do if we need to visualize things with, let's say we want to use an X and Y loop? How do we organize the location? So let's replace this with 2 for loops, one for the Y and one for the X. So we have Y equals 0 to 135. We have X equals 0 to 239. And so to poke these particular values, it would be to map these X and Y coordinates to the linear memory. It'll be X plus Y multiplied by 240. And if we run that, everything is great. So whatever our X value is, we need to take our Y value and multiply it by 240 to get which particular line we're at, and then we use the X value to move it in to that location. Now we're using poke 4. Let's say if we bring back in our little curve that we were working on earlier and just use an X and Y value to move something around. So bring it back to 120 multiplied by the cosine of t plus 110, and y equals 68 multiplied by the sine of t plus 60. This should give us a nice sine motion, and I'm just going to type these out fully. So this should give us a nice motion. Let's see what happens. So what we're seeing here is one of the differences between the pix function and the poke function. So let's just comment this out, and let's just go pix xy 2, and we get what we would expect. What is happening with poke? Why is it giving us this garbage instead of the nice smooth curve? And the answer is this here, mat.sin, mat.cos. The x value isn't too much of a problem because we're just adding x, but we're multiplying y. And the sine and the cosine are going to give us back numbers with decimal points. And when we take a number, even if it has a decimal point, 0.1, and we multiply it by 240, that number is going to be way out. We need to make sure that our y value is floored. So that's just something to look out for. If you're getting a lot of random movement or garbage when you're working with the poke function, just make sure that your value that you're basing your calculations off is actually an integer, or at least a number that doesn't have any fractional decimals on it. So that's how you update the VRAM directly using poke. What we're going to take a look at now is setting the palette. So I am going to adjust this lovely code here, and I am going to go back to I equal to 0, 0 to 32639, and I am going to set I equal to I mod 240. That gives me this lovely gradient that I'm going to use for testing the palette. So the palette resides at this memory location, and the palette is 16 RGB colors. So that is 16 24-bit RGB colors. And to set the palette, we usually use something like j equal to 0 to 47, and again that's 16 by 3, 0 to 47 do. And we will usually poke. So poke in this instance is going to be something that is the full byte, because we are working with RGB colors. So I can set every single color here, so 0x 3FCO, and let's say I want to make the most unoriginal TIC-80 palette ever, plus J, and now I have set every single color in TIC-80 to black. So all 16 of them, I have just wiped them out with 0, and I can do the same here and set it to 255, and now every single palette, every single color, if I comment this out, this is what you should be seeing, but I've overwritten every single color with white. Great. So one handy palette to know is just to multiply that by 5, and it gives us this nice black to white-ish kind of a shade, and we can trace what this is doing. So it's setting the first RGB color to 0 times 5, the next one is 1 times which is 5, and the second one is 10, so that RGB color is 0, 5, 10. Not exactly black, but good enough. And why are we multiplying it by 5? So 255 is the max value that we can use here. So if we multiply 47 by 5, we get a value that's close enough to 255 to give us that range of colors. So instead of the hexadecimal memory address for the palette as well, we can use 16320, and that will save us a character. The byte battle section on the sizecoding.org wiki, link in the description, has a range of different palettes that are ready to go, and you just have to set them up with a for loop like this. So for example, I'm just going to pick a random color from the Byte Battle page, a random palette, and it has them all organized by the length that they take. And if I run this, you'll see that we get this nice blue palette. But this first palette, also from the sizecoding.org wiki, is the basic black to white gradient that we saw already. So just to demonstrate this a bit better, that it is actually RGB components, I'm actually going to poke 16320 plus 0, and I'm going to set that to 255. I'm going to poke the same plus 1 with 0, and I'm going to poke the same plus 2 with 0. So 255 red, 0 green, and 0 blue. And that's after I've set the palette up here initially from black to white. So now I'm setting the first color in the palette to red. And you can see now that that has been successful. And you can set any RGB color that you want. You can go into Microsoft Paint and pick out a nice color and copy it in here painstakingly line by line. But you can see that the amount of characters that we're after taking up here just to change that one color to red, this is not optimal. There are other ways you can do things, and again, check out that Byte Battle page on the size coding wiki. So we're going to leave it there for today. Try and make use of these new functions in your shade bob today. So let's take a look at our shade bob in Pico 8. So the first thing that I've set up here is I have X and Y coordinates for my motion. So I'm centering it in the middle of the screen. I'm adding to it a cosine value of the time divided by 3.4 multiplied by 60, time by 2.2 multiplied by 60. These are just numbers, messing around with them to see what works. And the whole idea here is that you're essentially taking the sine and cosine at different rates. So you have different rates of the sine going up and down. It will be different to the cosine going left to right. It will still be a sine motion if you take it in isolation, and the cosine will still be in a cosine motion in isolation. When you add the two of them together, you get a much more complex behavior than just a simple circle. So I am going to plot this, and you notice that I have a CLS up here before my loop, so the screen is cleared once and only once at the beginning. And I'm going to set XY, I'm going to give it a radius of 3, and I'm going to give it a color of 2, and I'm going to run that, and we can see that we have our circle in motion around the screen. Now the circle is just the easiest way to visualize this motion for now, but what we need to talk about now is the actual shade part of the shade bob, where it actually does the additive blending, where it takes the colors that are there underneath the object and essentially increases them by 1. Now this is difficult to do with a circle, so what we're going to do is we're going to take a look at how we might draw a square pixel by pixel individually, because none of the built-in functions in Pico 8 have this additive blending mode that would allow us to add the color on top of, or to increase the color count by 1 at a certain pixel. So we are going to have a for loop. I'm going to use I and j for this because I've already used x and y. -4 to 4, j equals -4 to 4, end, and all I have to do is use pset, and that'll be x plus j and y plus I, because again we want to center it based on the x and y coordinates, and then we'll add the -4 to +4 in each direction. And I need to set this a color. I'll set it 2, and if I run this, we now have a square that is in motion around our lovely screen. The additive part is up to you though, so you have to figure out how do I add this color on top of it.